So picking up on our discussion of the electron arrangement around nuclei, this is a very helpful graphic because it shows you the relative energy levels of the electrons, the outermost electrons, around each of the elements. And so these are grouped. If you look down here, you have hydrogen and helium, element 1 and 2. And so those have 2 electrons. And those electrons are in a 1s shell, first shell level, and it's an s-type orbital. And you see that they're way down here. Generally, the energy of an electron by itself is considered to be 0. And so this is a highly negative energy level. That it's down in a well, and it's very close to the nucleus. And you notice then there's a pretty good energy gap. The next electrons for the next largest elements are going to be in a 2 shell in the s orbital, and there's a big energy gap here. As we move up, you see p orbital, 2p orbital, a gap, 3s, 3p, and then you notice funny things start to happen. The 3d orbitals have basically the same energy as a 4s orbital. The 4ds have the same energy as a 5s, and the 4f is much higher energy than the 5s and the 5p. And so obviously, if electrons are going to fill the lowest possible or available energy state, they're not going to fill in order 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4. Things are going to get jumbled because they're going to fill the lower levels. So the rules for filling and the rules for identifying the valence electrons are a little bit complicated. So we remember the basic rules. Electrons are going to fill the lowest energy state. We want the ground state arrangement. But we're really only interested in what's on the outside. We don't care about those 1s's and 2s's and 2p's necessarily, unless they happen to be the outer shell. So in chemistry, they showed you these wonderful quantum number rules, principal shell number, subsidiary shell number. These are the rules for constructing addresses for all the electrons, but they're tedious and not what we are going to do most of the time. They also show you a neat trick in chemistry for filling and placing electrons in the proper orbitals and getting the order right. But that's not as helpful as this trick. And the trick that I want you to be very comfortable with is to remember the basic rules here. And from these rules, then with a periodic table, you're going to be able to identify the valence shell very quickly. So orbitals fill from the inside. So we're going to get the lowest energy level possible. Shells are simply numbered 1, 2, 3, 4, 5, 6, 7. And then the orbital types, so you need to learn these 4 letters, S, P, D, F, in that order. So the way the orbitals get assigned, the first shell gets 1 orbital, and it's an s orbital. The second shell gets 2 orbitals. Now why? There's more room. The greater radius, your volume is the cube of the radius. There's a lot more room. So here we can put 2 electrons in this orbital. Now I got 2 in this s orbital and 6 in the p. The third shell, again, we're cubing the distance. We're moving farther out, and so I can get even more electrons in. And so it has, in the third energy level, 3 orbitals, an s, a p, and a d. And in the fourth shell, SPDF. In the fifth, you have SPDFs again, 6th, 7th. Again, all of them are theoretically possible. Now, notice the s orbital starts, the first s orbital appears on the shell 1, the first p orbital appears in shell 2, first d orbital in shell 3. And the first f orbital in shell 4. Now, when we go to the periodic table, the table is periodic because the elements in columns have similar chemical behavior. The reason they have similar chemical behavior is because their outside structure basically looks the same. And they're organized so that these all end in s's. The outer shell are s orbitals. These are all p's, these are all d's, and these are all f's. Now, you do not normally see the table this way. They take the lanthanides and actinides, the inner transition metals, they cut them out, and they stick them at the bottom of the page, and they glue these together here at barium and radium. And so these guys are missing usually. But this is the proper structure if you want to get the valence structure. You just have to remember the F's insert at the appropriate spot. So all you're going to do is identify where the element is. So let's say we're talking astatine here, element 33. All right, it's in the P grouping. 1, 2, 3 column, third column. So it's going to be a P3 orbital, a P orbital with 3 electrons in it. And it's going to be in the second, third, fourth shell. The p orbitals begin in shell 2, shell 3, shell 4. Now this gives you all of these little clues, n-1, n1, these are numbers. Ignore those. You're not going to have those on a periodic table. What you need to remember is that S's start in the first shell, P's start in the second. D's, these are on fourth row, but they start on the third shell. And F start in the fourth shell, even though they're on row 6. So just don't worry about these things. Just remember who starts when, and you can identify the structures. Now, if you look, there are some funky ones here that break the rules. And the reason they do that is there is a node of stability if the electrons don't quite follow the rule. In general, for the problems we're going to be wrestling with, you're not going to be worried about those. We're mostly going to be worried about the valence structure of nonmetals in particular. And then the interactions with metals in general will be, the metals valence structure is not as critical. All right, so a couple of practice problems here. Vanadium, what's the valence structure of vanadium? Okay, these are the S's, these are the P's, these are D's. And so they left gaps here, so you know these guys are inserted at this location. So we count, these are D's, 1, 2, 3. So this is a D3, a d orbital with 3 electrons. Which one is it? Well, the D's start on the third shell. So this is a 3D3. Calcium takes you over here. These are S's. It's an S2. The S's start on the first shell. So 1, 2, 3, 4. So it's a 4s2 valence configuration. You should be able to do the rest of these, and I would suggest you do that before you may pause the recording before you proceed. All right, that leads us then to one last feature of the atoms, and that's their electron attracting power. The nuclei are positively charged, and because all of the electrons are not on one side, they're scattered around. As an electron approaches a nucleus, it's always going to see a net positive charge from that nucleus. And some atoms will attract electrons much more strongly than others, and the primary reason they do that is that those electrons will complete an incomplete valence shell. So we can look at a table of, it's a periodic table. Now we're missing the lanthanides and actinides because we don't do a lot of chemistry with them. But these are the actual electronegativity values for the elements. And we're going to come back and use this table quite a bit in the next section. But anytime you are presented with a data set like this, there's a couple things you should be doing as you first encounter it. You need to look for patterns, and you need to look for extreme values so that you begin to get some fundamental appreciation of what the numbers look like. So we look, obviously the numbers over here are low. It starts low on the left, and they increase as we go to the right. Also within the columns, particularly over here in the nonmetals, they increase nicely as we go up the columns. Your highest electronegativity element is fluorine, and nobody else is close. Oxygen is the closest, and it's still only half a point, still a half a point away. Nitrogen, chlorine have the same electronegativities, and then you've got a number of other that have same electronegativities here in the nonmetals. And you notice quite a range, 0.8, 0.7 being your lowest, and the metals range really from 0.7 to about 2.2. There's a few, there's a 2.2 or 3 or so here. There's a gold is a 2.4. So we see some patterns. Most of the metals are around a 2 or a little less, and then the nonmetals get up here. And fluorine is in a category all its own. As we get into polymers, you'll learn this part of the periodic table just because we spend so much time with those elements in building polymers. Okay, so that's electronegativity. Now the question, one of the questions would be, why does electronegativity increase in the direction it does? Well, the halogens, this last column before the noble gases, have the highest electronegativity in general in all of the rows. And the reason for that is they really only need one more electron to become, at least in terms of their electron structure, noble gases. So fluorine is like the Corvette collector that has all of the Corvettes ever made, one of each except for one. And so he goes to auction, and he really wants that one because it finishes his collection. And so there's a high affinity here. And fluorine will will grab electrons. And all of these have this similar affinity. Now, you say, well, okay, iodine has the same need for one more. Why doesn't it have a higher electronegativity? The problem for iodine is it's element 53. So, yeah, there's 53 protons in the nucleus, a lot of attraction. There's also 53 electrons. And so any approaching electron is going to see those screening electrons, they're called, and going to be repelled. And so the net attractive capacity for iodine is small. Fluorine is very small, only a few electrons. There's almost no screening effect. And so the nucleus is virtually uncovered most of the time. And you're going to have very high attraction for that. Okay. So the periodic table can be broken into families. You should know the general properties of those families. In particular, you should know the boundary for the nonmetals, okay? And we'll be developing this much more in the next discussion, but nonmetals follow diagonal, okay, and everything in this triangle. And then, of course, the noble gases. And then these are an interesting group. They're called poor metals, and it's because not that they're not metals, and it's not that they don't have money, but that they don't have all of the properties in all of their glory that most metals have. So titanium, for example, is a poor conductor as metals go, and so on. So bismuth has a low melting temperature. In fact, several of these, tin, lead, bismuth, all have very low melting temperatures. So they are not really metallic metals. And then in general, the alkali metals and alkali earth metals are going to be notable because they're going to form very, very polar bonds with nonmetals. These guys love to give away electrons, and they're going to be very good at that. And we'll see that in the next section.